Welcome everyone. Thank you for turning up to this. This is a project-specific webinar, obviously about To-Syn-Fuel. The To-Syn-Fuel project's entering its last 4 months now, so it's an exciting phase for the project. And so we'll give you some presentations about the status of the project, particularly about the demonstration plant that's running at the moment. So without further ado, I'll hand over to Robert Dashner, who will start the presentations. Over to you, Robert.
Hello, everybody. I'm going to share my screen first. Can you please give me a sign if you can see the slide?
Yeah, that's good.
Perfect. Yeah, dear visitors, I'm really happy to share today a very brief introduction of the To-Syn-Fuel project. I have the honor to coordinate this project, and as Mark already said, we're in the very last stage of this project, and happy to share a few results, a lot of results already, even if a few things are in the finalization stage. But I think it's really a lot what we achieved in the last 4.5 years already. At To-Syn-Fuel, the project is on the demonstration of waste biomass, synthetic fuels, and green hydrogen. And as illustrated in this picture, what we're doing is to bring, in the specific case of sludge from wastewater treatment plants, to make this into a standardized fuel and drive mobility with this. And this, well, is part of this project since May 2017 and will end this September. And it's a team of 11 partners from 5 different countries, and most of them are present today in this workshop. And I'm really happy to introduce this. What I want to give you in the next few minutes is a short overview about the project in general. Well, what are the specific goals? There are 2 things. The one thing for sure is the technical part, really to go for the production of green hydrogen and green diesel, green gasoline from sludge as a showcase. This is an important step from the technology point of view to really bring this forward. But on the same side, it's the other non-technical issues has the same importance. Like we are working on the business modeling, also on the life cycle assessment, and all this dissemination activities, socioeconomic activities. So a lot of things going on, and some of the results or intermediate results we will hear today, and I'm really happy to start this workshop. Well, as mentioned here, some of the key indicators is I think important also to see the scale of this demonstrator. There is the goal to have up to 2,000 tons of sludge converted in a unit which makes around 300 kilograms per hour of dried sludge. And this is, well, can I say already this, we exceeded this. We will have a capacity of around 400 to 500 kilograms per hour and processing around 10 tons per sludge per day. And this leads to, well, a lot of product. The goal is up to 200,000 liters of this Tcr crude oil, which we'll see later on. But from a demonstrator point of view, what is the approach? As mentioned, we're going with this feedstock, processing in the so-called Tcr technology, which is a pyrolysis-based technology to produce a syngas and a bio-oil. And the syngas is then, well, is hydrogen rich. We will hear later on and see also the live stream from our demonstrator in Germany. And with a PSA technology from our partner Hygiene, we can separate the hydrogen, and hydrogen is used in situ for the upgrading of the crude oil, which is produced in the process. And here we go with this hydrogen treatment process to a biofuel or a sustainable fuel in the end. So this is a very brief overview, because the colleagues will show you more in detail, and as well as a live stream from Hohenburg, that the unit and also the product that you can have here, and, well, a live impression where we are and what has been achieved in the last years. Maybe a little bit more insight on the project. So we have 3 main parts. The first is a part of the practical demonstration. For sure, there was a very massive part to the plant design and assembly of all this demonstrator we will see later on. You can imagine, due to all the COVID situation, it was not that easy, but we did it. So since last year in summer, the unit is in operation, and this plant demonstration is going on. And in parallel, the work package for the fuel demonstration also is going on, and we will hear first results from University of Birmingham and ENI later on. As already said, beside the technical part, we had a very important part of the assessment of the project and the products. And this is to be seen here. I said already, there's a social sustainability. We will hear later on a speech from the colleagues of LATAT, and also the LCA will be shown today from Uni Bologna. And yeah, the business modeling is ongoing, and well, more than internal things like the regulatory issues and the risks has also been assessed. And last but not least, for sure, the exploitation and dissemination is really important, and also to be party of the European Biomass Conference to really show our results is what we're going for as well. Yeah, this is already the major part of my introduction. And as last, I want to give you just two pictures. The one is the demonstration site, as said, in Hohenburg. It's a very small village in Bavaria, in Germany. But what is really impressive is the inner look of the demonstrator. And on this picture, you can see what the actual status of the demonstrator with the whole value chain just shown in principle. Here's the TCR technology for the sludge conversion. There's a product gas drain to separate the oil, the gas, and the char. And then there's the hydrogen separation as the PSA, and then the final step, the upgrading of this crude oil with the separated hydrogen to sustainable fuels. And this is already my very brief introduction. Well, maybe also a very short summary where we are and what we already achieved. As said, the demonstrator in Hohenburg is in operation since last year in summer, for more than 1,000 hours of operation, and a few 10,000 liters of crude oil has already been produced. All the components has been commissioned, and the very last step is also going to be finalized now. It's the commissioning of the HDO plant, but here we will later on more details from the colleagues. And also, I think I said already, we'll hear some intermediate, already some final results regarding the LCA today, also the product qualities and so on. As said, the sustainability and also the business modeling is not, I think, not part of the speeches today and this workshop, but we also have very promising activities started, which was only possible due to this demonstrator. For example, there is already a licensee from the TCR technology. It's a big refinery in Canada, and there's also another refinery partner here in Germany, which is at the moment very forcing its activities to go for sludge treatment in Europe. So, and then, well, I don't want to talk too much about that. And there is one big highlight at the end of the project, the European car tour. And this will be, I think, part of this workshop in the end. So yeah, that's already it from my side. And now I'm also looking forward to the part of the colleagues. And thank you so far for your participation.
Thank you, Robert. I forgot to say at the start, if you have any questions, submit them onto the chat on the EUBC platform, not within Zoom. I don't think you have access to the chat in Zoom anyway. So I suggest, as the detail is coming from the next presentations, to put your questions related to those. So we'll move on to the next technical presentation, which is Maulud Ouadi from University of Birmingham. Over to you, Maulud.
Can you see the slide?
Yep,
okay.
Yep, that's okay. Good.
So thanks, Robert. So Robert presented to you the demonstration site. So to understand what we have, first it's important and necessary to characterize all plant inputs and all plant outputs. So first I'll present the plant inputs, so the feedstocks going into the plant and the biochar. And then later, Stefano from ENI will present the bio-oil characteristics and the properties of that fuel. So first of all, in total, the TCR can process a wide range of lignocellulosic biomass. We like to target waste biomass and non-food competing biomass, and we've tested over 50 different types of feedstocks at pilot scale, both in Fraunhofer, Umsicht, and at the University of Birmingham. It's always necessary to do some pre-treatment to the feedstock, and the pre-treatment steps are usually drying, granulating, and pelleting. But for this particular feedstock, sewage sludge, only drying was necessary. And 4 products are always produced from the TCR. That's a bio-oil, which is phase separated, a water phase, a syngas, and a biochar. So the pre-treatment, although some wet biomass can be processed, and we usually say up to 28% moisture can be processed by the TCR, it's important that it's dried to maximize process thermal efficiencies. And for this project, the sewage sludge was dried to less than 5% moisture by the company E&T Achenberg in Hornburg, which is a drying facility next to the demonstrator site. So they basically dry sludge from regional municipalities. They use state-of-the-art belt drying technology, and the heat for those dryers are provided by a wood gasification unit, which gasifies wood pellets. Around 36,000 tons of dewatered sludge is dried at that facility per year. They have 2 lines of operation, and they have a drying temperature which is below 100 degrees Celsius. So although, so as received, so the feedstock we received was after drying. We received in total 13 batches of dried sludge, and the average was taken of all those batches. And here what you can see is the elemental composition. So the carbon hydrogen contents were within similar range to what you would find as typical sewage sludge from other research findings. We have a presence of nitrogen and sulfur components in the feedstocks, and they're unwanted components in any feedstock, as it usually leads to downstream emissions. Similarly, we tend to find when we have a lower oxygen content of feedstock, that usually leads to a better quality bio-oil being produced. Proximate analysis was also performed, and that's necessary in order to simulate the thermal degradation behavior of the feedstock during the TCR process. And with the proximate analysis here, what you can see is that the sewage sludge contains a relatively high amount of ash and low amount of fixed carbon, which leads to a calorific value, which equates to approximately half that of an anthracitic coal. So next we did an Icp Metals Analysis. So the sewage sludge was further analyzed to detect all the metals present within the ash. The main metals detected were calcium, iron, phosphorus, aluminium, magnesium, and potassium, and silicon. Most of those are catalysts within their own right, and they have a catalytic function during the TCR process, which promotes the deoxygenation of bio-oils and also to some degree the formation of hydrogen in the syngas. Some heavy metals were detected, although most fell within the EU limits for soil improvers, such as chromium and nickel. Zinc and copper fell slightly outside the limits. So after the TCR process, the biochar was again analyzed, and here what you can see are the elemental results, and that's plotted against the Van Cravelen diagram. So what we can conclude from this is the TCR was effective in bringing the biochar elemental ratios closer to an anthracitic coal compared to the original feedstock. The hydrogen and oxygen from the feedstock was mainly transferred to the gases and bio-oil, as well as some of the nitrogen and sulfur components. And the biochar has a much higher ash content than the feedstocks. Most of the volatiles were removed, so you have a very stable biochar at the end, and this leads to, due to the higher ash, it leads to a lower calorific value biochar, which was half that of the original feedstock. So again, what we did is the metal ICP analysis of the biochar, and we measured that against heavy metals for use as a soil improver, and the biochar was within limits for most metals, including mercury, chromium, nickel, and lead. The biochar fell slightly out of limits for cadmium, copper, and zinc. However, only one batch has been so far analyzed, so we can't draw any firm conclusions from this until we analyze further batches. So that is the biochar, and that is the end of my presentation. Thank you, and if there's any questions, please type them in the chat.
Okay, thanks, Maulud. Currently no questions submitted at the moment, but if you think of anything, please still submit your questions because we can try and answer them towards the end as well. So yeah, feel free to add questions as they come up. Right, next presentation is from Stefan Eder at Fraunhofer. This will give you an opportunity to see a lot more about the demonstration plant. So Stefan, if you're ready, I'll hand over to you. I think you're on mute at the moment.
So, hello everyone from my side. I'm here live at the production hall in Homburg, Bavaria, Germany. And I will bring the core components of the To-Syn-Fuel plant to you, and I will show you directly on site how the demonstrator is looking and how the functionality is. So first question, can you see my presentation already? Perfect. Yeah, so presentation is about the fully assembled and integrated demonstration plant. And yeah, as you have already seen this picture before at my colleague's presentation, I will just skip it and come directly to the first core component, that is the feedstock. So the feedstock is coming from the drying facilities next door, that and our feedstock buffer is loaded every day by front loader, as you can see on the picture. And we are processing the feedstock then in the next core component of the plant, that is the Tcr 500. And yeah, the Tcr is Thermo-Catalytic-Reforming, and it's a two-stage reactor system. And at the first reactor stage, we have an intermediate pyrolysis where the feedstock is heated up in absence of oxygen to around 400 to 500 degrees Celsius, and therefore pyrolyzed, and with a retentioning time of about 9 minutes. And the vapors are formed and separated from the char. The char then is falling into a second reactor stage, the catalytic reforming. And as you already have heard previously from my colleague Milu Duadi, it's working as a catalyst there for the vapors that are forced to flow through the char bed and are then again heated up to temperatures between 500 and 700 degrees. And then the products of the TCR plant are formed, the carbonisate, the Syn Gas, the oil, and the water. What is important to say about the post-reforming or catalytic reforming step is that in this reactor step, we are reducing chars and long carbon chains to have really high quality products in the end. and we as well gained a high hydrogen value within this component of the plant. We have hydrogen values of up to 30 to 40 volume percent. This depends on the feedstock and on the temperatures that are that the plant is operated at. And yeah, on my next slide here, you can see the demonstrator, a picture of the demonstrator. So here on the right side of the picture is the Tcr reactor, and below it is the post-reformer and the combustion chamber. And on the left side of the picture, there's the pyrogas train, where the gas is further processed and cleaned after the 2 reactor steps of the TCR plant. This pyrogas train is made of several cleaning steps. So first, we have a 2-stage dust cleaning, hot gas cleaning, to remove dust from the gas. And first is a multicyclone, as you can see on the right side of the picture. And downstream the multicyclone, there are 2 ceramic fiber filter bag filters to reduce the fine components of the dust from the gas. And after this hot gas cleaning, the gas or the vapors are cooled down in the condenser to separate the permanent gas from the oil and water. And the oil and water is then pumped into a oil-water separation tank that is a graphimetical separation where the oil and water are separating themselves, and then we can get the final product, oil and water, from this tank. And the gas is further cleaned by a gas scrubbing step to reduce ammonia content, and 2 electrostatic participators to clean the gas from aerosols. In these pictures, you can see the Char extraction system, where the carbonisate is extracted from the system, from the post-reformer. This Char extraction screw is an inner tube cooled and jacket cooled screw to cool down the Char from temperatures of around 600 degrees Celsius to temperatures below 80 degrees Celsius. Downstream this extraction screw, we have a sluice system, a chain conveyor, and in the end, the Char silo to store the Char. Okay. Here's some impressions from gas monitoring. So as you can see, the hydrogen within the gas we have measured here is the hydrogen ratio of this gas we have measured there is about 31% in volume, and with a higher heating value of 14 to 18 megajoule per cubic meter. That also comes from the hydrogen as well as from the high content of methane in the gas. And there's as well, the other main components are CO2 and CO. The gas from the TCR plant is already engine ready, as it is clean from aerosols and it is dust free. So this is most important. And yeah, it's and as the H2S and ammonia ratios are clean from the gas as well. Here we have some impressions of the Tcr oil we are producing here on site. That's of low viscosity and low polarity, and it has as well a low water content and reduced functional groups. And yeah, most important is that it is thermostable, what opens the pathway of hydrotreatment. And yeah, here is analysis of the picture of the carbonisate. And yeah, the Char consists out of around 75% of ash, and all minerals, for example, phosphorus, are encaptured. And yeah, possible heavy metals have to be analyzed, as Milot already taught in this presentation before. And yeah, optional for the char is energetical use, for example, by a gasification process as well. And heating value of the char is about 9.5 megajoules per kilogram. So now that you have heard about the TCR core component, next step is for the Syn Gas, the PSA system. And this PSA system is to separate hydrogen and from the Syn Gas that we're producing in the TCR 500. And therefore, to bring you this core component closer to you, I will hand over the word to a colleague from the Netherlands, from High-Gear, Dick Lifting. And yeah, Dick, it's up to you.
Thank you, Stefan. Good afternoon, everyone. Thank you for joining this webinar. And I'd like to talk to you a little bit more about the PSA, like Stefan announced already. So when the gas comes out of the TCR, it will first will be compressed in a Syn Gas compressor, which you see on the right, on the left picture. So there the Syn Gas is compressed to about 10 bar, and in that then afterwards it goes into that white container which contains the PSA. PSA is designed and constructed at High-Gear. It's one of our key products in hydrogen production systems, and we use it here for the hydrogen produced from TCR and from the HDO recycled gas. So if you go to the next slide, Stefan. Then what our challenges is are in this project is that we have TCR gas coming from the TCR and hydrogen coming back from the hydrodeoxygenation, which you will be told more about in a few minutes. And this hydrogen is a valuable product, so we want to separate it from all the other components and use it, or as hydrogen for the treatment in the hydrodeoxygenation reactor, or as hydrogen for other applications, for instance, use in fuel cell, in cars or other fuel cell applications. So that means that with the changing concentrations and flows of the hydrogen and Syn Gas coming from the TCR and HDO, we want to make sure that we get a constant high purity hydrogen flow out of the PSA, and we designed our systems to it based on the hardware we've designed and controls that this PSA is being operated with the fluctuations of the feed flow and the concentrations to get a fixed output and a high purity output, and that's fully automated. So there's no influence of a operator turning knobs, but it's fully automated based on the concentration measured in the hydrogen stream, product stream, and we can change the settings of the PSA based on the measurements we do in the system ourselves. Yeah, the next slide, please, Stefan. So briefly, what is PSA? PSA is a separation process based on variation on the absorption parameters of gas species on a specific solid. Lots of solids which are used are activated carbons or zeolites or aluminas, that type of materials, porous materials, which absorb CO, CO2, methane, and all the other components, but not the hydrogen at high pressure. So you enter the Syn Gas at high pressure to the PSA, hydrogen comes out at high pressure and goes to the hydrogen buffer, and all the other components are absorbed in the PSA vessel for some time, until it's the first component is almost breaking through, and then you switch off this vessel and go to the second vessel and start the production of clean hydrogen in that second vessel. And while you're producing that in the second vessel, the first vessel is cleaned again, so you leave off the pressure, hence pressure swing adsorption. You swing the pressure to a low pressure again. We apply also a vacuum to it to even get the low concentrations of impurities out of the PSA bed. And then after some time, it's ready to be used again in the adsorption cycle and producing hydrogen again. Well, to have this timing-wise, the adsorption and the desorption of those gas species, to have it in the timing right, we use 4 vessels. So there's 1 vessel always in production, and there are 3 other vessels. We are in different stages of pressure, of cleaning up. It's purged. There's cleanup by vacuum suction, and so with making the timing of the processes in each vessel coincide, we can have a continuous flow of hydrogen out of the PSA. Well, a brief, short picture on typical yield purity plot. You see here on the left the yield on the horizontal axis, which can be reached is over 90% of the hydrogen. So that's the amount of hydrogen compared to the amount of hydrogen going in. So the hydrogen, you can get to about over 90% of yield of the hydrogen out of the PSA with a certain purity, and this purity is given in 2.0 up to 12.0, and this is the amount of 99.999% of hydrogen, so the purity of the hydrogen. So a purity of 5.0 means that it's 99.999% pure hydrogen, so 10 ppm of impurities in the hydrogen product. So what you see in this plot, which is based on modeling, but it's been proven in the meantime by experiments, that with a vacuum applied of 0.15 bar, you get at the same yield, you get a higher purity than when, for instance, when you use at a vacuum pressure of 0.4 bar. So it just helps to clean up the bed again after you have adsorbed all the undesired species in the PSA. So therefore, we use the VPSA and go to a low pressure of 0.2 bar in this in our PSA here in Homburg. So next slide, please, Stefan. So we've built a system. We've designed it. We built it, and you see here on the right, you see a picture of the 4 vessels which are doing the PSA, the hydrogen cleanup. Well, there's the input and output, as we already described also by Stefan. The Tcr gas has around 35% of hydrogen. The hydrogen deoxygenation recycle has a somewhat higher concentration of hydrogen still there. So in the end, there's about 70% of hydrogen going into the PSA, which needs to be cleaned to this purity of 99.95, which is good enough for the HDO, and 99.999, which is, for instance, the fuel cell quality we can generate. Well, as I said, we have this 4-vessel PSA. We've designed it and constructed it at high gear. We have the controls developed and installed on a system, and we can operate the system. It's CE certified. It's designed after PED regulations, so it's safe to operate it. And so we built it in Arnhem in the Netherlands, and we shipped it to Homburg, Bavaria, where it has been installed by Stefan and his team. So next slide, Stefan. The first results of the PSA, you see in the plot the cycles, the pressure swings. So in yellow, that's just for 1 vessel. You see what's happening. So the pressure is at 10 bar, where we're producing the clean hydrogen. And at some point, we switch off the pressure for this vessel, and you see the pressure goes down. There we desorb all the other species, and you see at the same time another vessel is in production at the 10 bar pressure. And in the meantime, this yellow vessel is being cleaned, vacuumized, and then at some point it's waiting to be ready again for its next phase of hydrogen production. So showing this plot means that we have run the PSA. This is actually actual data from the PSA in Homburg with TCR gas. So we've operated, it worked well, not a very long time. And typically a PSA needs some time to be equilibrated and to make sure that all the adsorption and desorption are equilibrated well at the same time. So we need some more time to really get to the very low concentrations of carbon monoxide. We've seen 10 ppm, so coming from 7% down to 10 ppm, we reached that already, but we're still going down once we have to shut off the PSA. So the first results look very good. We reach all the desired pressures. We see the low CO concentrations, and that means that also the other gas compositions are low, because CO is the most difficult one to capture. So yeah, we're ready to operate further, getting the gas into the system and clean it up to produce the clean hydrogen. This is my presentation. Thank you for listening in, and if there are any questions, then I'll be happy to answer those. Thank you. Back to you, Stefan.
Okay, we're about 5 minutes over, so if we can just bring this bit to a close, please.
Yep. So I'll come back. Thank you, Dick, for your presentation about the PSA system. I will shortly introduce the HDO system to you, and then we have a walk through the production hall. So after the hydrogen is separated from the syngas by pressure swing adsorption, it's feeded into the HDO plant together with the bio oil from the TCR, and to further process this and upgrade this to the hydrotreated bio oil, the HBO oil, that you can see on the right side of this picture. And this HBO oil is then already a mixture of fuels, and by distillation you can, for example, get then the diesel that already meets the Euro norm, or raw naphtha and kerosene, for example. And yeah, here you can see, have an overview where the HDO plant is located in the production hall. And yeah, the HDO is at the moment in commissioning phase, and it is built made of 6 reactors to upgrade the bio oil to the hydrotreated bio oil. And so that's it so far for the core components. And now I will show you the products and give a walkthrough. Close my presentation for this, and here you can see, for example, the Tcr oil, and this is oil that we have produced here in these facilities. And this is hydrotreated bio oil made of oil coming from TCR 500 from Homburg as well. But it's not hydrotreated here in Homburg. It was hydrotreated in our lab scale plant. And this is diesel from this hydrotreated plant. And gasoline. Yeah. So now I will show you the TCR 500 and the PSA system, as well as the HDO. So the overall To-Syn-Fuel plant live here from the production hall in Homburg. First of all, here we have the TCR 500 Auger Reactor with a length of more than 12 meters. Screw length is around 8 meters, and it's rotating with rotational speed of around 3 rounds per minute. As I already said before, the char is then falling down in this post-reforming step, where it's further processed and working as a catalyst, and together the gas together with the char is then upgraded to this to get this high quality products that we achieve from the plant. The plant is heated by flue gas made from propane combustion. And here in these channels, you can see this is the heating channels where the gas is entering the system and heating it up. And yeah, below here, down here, it's a Char extraction screw where you have seen a picture before. And here we have the multicyclone and the ceramic back filters to remove the dust from the syngas coming from the TCR 500. In the back here, we have the condenser. It's maybe a little bit hard to see behind all these pipes, and where the vapors are cooled down to ambient temperatures, and oil and water is separated from the permanent gas, and then the gas is entered to the gravimetric sedimentation tank that you can see here, where separation tank where the oil and water is separated. And yeah, then we have here our process water storage, where the process water from the separation tank is stored then. And we so to have a further look here, this is where the gas is leaving the TCR 500 plant and coming out there from this pipe, and then it's fed into the Syn Gas compressor to compress it up to to pressure of around 10 bars to feed it into the PSA system that is located here inside this white container. So already seen pictures before. And then in the back we have another compressor for the hydrogen coming from the pressure swing adsorption, but pressure is pressurized up to 140 bar, and then feed it into the HDO plant that you can see here. And together with the oil from the gravimetric separation tank and the hydrogen from the pressure swing adsorption, these two components are processed here in the HDO plant to form this hydrotreated bio-oil. So yeah, this is all from my side for the moment. If you have further questions, please feel free to ask them. I will go back to the place where I've presented before, and then I can answer your questions.
Thanks, Stefan. We've got some questions coming through on oil properties that might come up in a later presentation. Stefano, did you want to, that's Stefano Kibegi, did you want to address that in your presentation?
Yes, I will try, even if the measurement of the TCR oil viscosity wasn't done by us directly, but okay. Apparently the crude, let me just share my screen first.
Are you next? Sorry, let me just check. Are you?
Yeah, yes.
Okay, perfect. Yep. So that's good timing. So Stefano will talk through the characterization of the oil, which may answer your questions, Paolo.
Okay. Yeah, this is, I will present the work of characterization that was carried out by E&I in the project and in the research center of Novara, which is the renewable energy center in Italy. We perform a very detailed characterization of the TCR oil, and this is quite important in view of its use as a fuel, especially also to optimize the hydrotreating of this TCR oil. These are the analyses that were carried out. So we didn't do, as I said before, to answer the question, we didn't do directly the viscosity measurement, but from Birmingham, they provide me the value of 10 at 40 degrees C. So it's a very low viscosity oil. And this was also found by us by by the analysis we carried out. We first of all perform elemental analysis, and we confirm a pretty high value of nitrogen and oxygen. So this must be then reduced in the hydrotreating. But on the other hand, we have a very low value of inorganics, of ashes in the TCR crude. And on the right here in the chart, you can see the amount of inorganics is pretty low. It's just few ppms for some of them. On the other hand, we have an average of around 10 milligram of potassium hydroxide per gram. So the acidity that was measured using a potentiometric titration that is usually performed for crude oil. So this value is a bit higher than an average crude oil, which has around 2 of a total acidic number. On the other hand, we then perform a more detailed characterization using mass spectrometry analysis. And first of all, we perform Gcms analysis. And in this diagram, you can see the application of the different mass spectrometry techniques according to the molecular weight of the compounds and the polarity. So Gcms was used basically for the most volatile and less polar analytes. And on the other hand, as a complementary and more powerful technique, we employed Fourier transform ion cyclotron mass spectrometry using APCI ion source, which can then detect and determine the more polar species. And this very powerful high resolution mass spectrometry technique can also give a name to thousands of different species, different compounds, organic compounds present in the sample. Just to give you an overview of the Gcms analysis, you can see that we have a quite complex composition. So some of the peaks could be actually separated, but we have a big coelution. So chromatography cannot separate all the compounds present in the mixtures. The most important and most abundant species were found to be saturated hydrocarbons with in a range from C12 to around C25. And also we found some nitrogen-containing compounds as long saturated nitriles. We then perform, as I said, Fti Crms analysis. With this technique, we confirm that the oil has an average molecular weight of about 200, so it's not that heavy. But also we could determine, separate, and give a name to thousands of different peaks. And to each of these different peaks, we could assign an elemental molecular formula. So that was a petroleomic approach we employed for this Tcr oil. And this is the result. So we then give a different color for the species containing an increasing amount of nitrogen and oxygen in the elemental formula. And this is just an overview of the classes. We then classified the species according to the number of heteroatoms present. So basically the most abundant species found were the one with 1 to 4 nitrogen and species with both nitrogen and oxygen. With this technique, we can go into even a deeper detail, and I just show you how. So we then plot each different class according to the number of carbon and the number of double bond in each molecular formula we could determine and could assign. And this is a way to figure out which might be the main structure present in the oil. So most of the species for this class show a dBe value over higher and above 4, which is can be considered as aromatic. So most of the species are heteroaromatic species, but with a number of carbon which is compatible to short alkyl chains linked to this aromatic course. And just to give you an example of the comparison between the Tcr oil and the crude oil, and on the right we have a distribution of species for hydrocarbons in the crude oil, and the same class, so only carbon and hydrogen for the Tcr oil. As you can see, the distribution is located in an area which the carbon number is much lower, so around 50 to 25, whereas for the crude oil, average crude oil, we have much higher molecular weight species with much higher carbon numbers. And This results was also confirmed by NMR, carbon-13, and this is the carbon-13 NMR of the Tcr oil, in which we could determine the main carbons present in the mixture that were found to be aromatic and aliphatic carbons. By the ratio of the aromatic and the aliphatic carbons, we could determine this factor, which was found to be 0.45, which is much higher than a crude oil, which is usually around 0.2. So that means still we have relatively high aromatic content with a short aliphatic chain linked to the aromatic cores. Just to end the presentation, so we found that this is a summary. So we found that the TCR has a medium light boiling point, very low hash content, and a total signal number a bit higher than an average crude oil, which is around 2. So HDO should be optimized and employed in order to reduce both the acidity and the nitrogen and oxygen as well. So by GC and GCMS, by mass spectrometry, let's say, we could find a very high complexity of the TCR oil, but we could also determine most of the species containing nitrogen, which is quite useful in order to then optimize and develop the hydrotreating that in order to then produce the final fuels. NMR confirmed these findings, but we are confident that HDO will reduce the nitrogen and oxygen and also the acidity in order to obtain a fuel of good quality. And this is something we're going to do next in the project. With this, I would like to thank you for the attention. I hope I replied to the question, and I'm available to other questions if they are from the audience. Thank you.
Okay, thank you, Stefano. I see Robert is answering the question related to viscosity in the chat. So, and as I said, as time is quite compressed at the moment within these presentations, if you'd like to come over to our project booth and ask questions there, we can do that as well. It gives us a bit more time and space to answer. So we'll move on to our next presentation. Thank you, Stefano. And this is Serena Righi from University of Bologna, who will talk through the greenhouse gas emissions and LCA. Over to you.
Can you see my screen?
Yes, that's great.
Okay, thank you, Mark. Good afternoon. I'm going to present you the greenhouse gas emissions of the To-Syn-Fuel technology. The red 2 states that the greenhouse gas GHG emission savings from the use of biofuels shall be at least 65% from the 1st January 2021. Therefore, one of the most important aims of the To-Syn-Fuel project is to verify that the target required by the Renewable Energy Directive are achieved. The RED 2 offers a formula, as you can see, to calculate the emission savings. And therefore, as you can see, we need to know the total emissions from the biofuel and the total emissions from the fossil fuel comparator, that are 94 grams of CO2 equivalent 4 megajoule. The RED 2 states also that the total GHG emission shall be calculated throughout the entire life cycle of the biofuel. Therefore, from the extraction or cultivation of raw materials to the use of biofuel. Moreover, it is possible also calculate the emission savings from soil carbon accumulation, from CO2 capture, etc. It's important to highlight that the RED 2 says that waste and residues shall be considered to have zero life cycle greenhouse gas emissions up to the process of collection. And this is very important since the feedstock of the To-Syn-Fuel process is sewage sludge. In order to calculate the greenhouse gas emission of our project, we have applied the life cycle assessment method. The LCA is an ISO standardized method organized into 4 stages: goal and scope definition, life cycle inventory, life cycle impact assessment, and interpretation. In our study, the goal is to assess the greenhouse gas emission savings by the demonstrator located in Hamburg, and which treats 500 kilos per hour of dried sewage sludge. The functional unit is 1 megajoule of fuel, and we have considered 3 scenarios which differ in terms of additional thermal energy provided for sewage sludge drying. In the first scenarios, the additional thermal energy is provided by natural gas. In the second one is provided by wood gasification. And in the third one, we don't have additional thermal energy since the drying is provided by greenhouse. Each scenario has been compared with conventional fuels and RED 2 saving target. The system boundaries are from sewage sludge transportation and treatment to the distribution and use of biofuel. Boundaries include, as you can see from this figure, thickening and dewatering, and also drying of sewage sludge, sludge transportation, Tcr PSA HDO system, the treatment of HDO oil in order to obtain the biofuel, its distribution and use. Moreover, we have included also the wastewater treatment plant in order to treat the wastewater, the biochar gasification in order to obtain energy, and the phosphorus recovery from ash coming from Char gasification. The inventory data are primary and secondary. The primary data are mainly from Hamburg demonstrator, and they are about Tcr PSA HDO system. Secondary data are from the LCA databases Sfera and EcoInvent, and they concern sewage sludge treatment, Char gasification, phosphorus recovery, and wastewater treatment plant. Here you can see the results. GHG emissions of biogasoline, the 3 first columns, versus conventional gasoline, the 4th column, and RED 2 fuel comparator, the last column. You can see also the orange line. It is the benchmark set by the RED 2, and it is about 33 grams of CO2 equivalent per megajoule. As you can see also from the figure, in the first scenarios, we don't reach the target set by RED 2, but in the second and the third scenarios, the results are very good. This table presents the GHG emission savings of the three scenarios. We have also calculated the contribution of the different biofuel life cycle processes. And you can see that the contribution of the phosphorus recovery in orange, it's very important because this process help to saving greenhouse gas emissions. We can see also the green bar in the first scenarios. This is the drying of sewage sludge, and we can see as this is the most important contributor to the emission of CO2 and other greenhouse gases. In conclusion, the wood gasification and greenhouse scenarios achieve the RED 2 target, while the natural gas scenarios doesn't reach the target. The drying of sewage sludge is the main contributor to GHG emissions in the natural gas scenarios. In contrast, the contribution of sewage sludge drying is negligible in the wood gasification scenarios because in this case we have biogenic CO2 emissions and they are considered carbon neutral. Obviously, we don't have the contribution of drying of sewage sludge in the greenhouse scenario. In the future, the use shifting towards more sustainable thermal energy sources for sure will reduce strongly the GHG emissions of the To-Syn-Fuel technology for all the scenarios we have considered. And finally, phosphorus recovery from gasifier ashes is the main contributor to the GHG emission savings in all scenarios. Therefore, it will be very important to combine To-Syn-Fuel technology with the phosphorus recovery system. Thank you for your attention.
Thank you, Serena. We have no questions on the chat at the moment, so if there's anything you want to ask or comes up in the next 10 or 15 minutes, just put a question in the chat now and we'll answer towards the end. So thank you, Serena, and we'll move on to our next presentation, which is Ariadne Claret about the social impacts. Ariadne. She's coming. Hello. Yep, that's good.
Could you see the screen?
Mm-hmm. Yep, that's good.
So good morning to everyone. I'm going to present a little bit the work performed in the To-Syn-Fuel project related to the social life cycle assessment of the technology and the products that the technology have been developed. First of all, I want to explain and remark a little bit the main objective of this research, which is to evaluate the socioeconomic impacts and benefits of synthetic fuels on local and regional stakeholders under the Tcr PCA plan on the society and on the economy using a life cycle assessment perspective. So the methodology used to do this research and to fulfill with this objective is the social life cycle assessment methodology, which is a methodology developed by United Nations Environmental Program and the Society for Environmental Toxicology and Chemistry. In order to apply this social life cycle assessment into the project, I have been following the guidelines for social LCA of products and organizations, which are represented here in the left figure. These guidelines have been updated on January 2021. On the right figure, you can see a little bit the different stages, the 4 interrelated stages in which the social life cycle assessment will be performed or are being performed. And it is important to remark that although social LCA is not a standardized methodology, it is in large part based on ISO 40040 and 40044 framework for environmental life cycle assessment, which has been explained before. So these 4 stages are the goal and scope, the social life cycle inventory, the social life cycle impact assessment, and the interpretation of the results. Now I'm going to summarize a little bit these steps, and after this I will focus on the steps in which I'm working right now related to To-Syn-Fuel project. So the first one, the goal and scope, is the step where the specific questions needs to be tackled and answered in order to know which are the main aspects that we want to tackle with the social LCA. After this, we need to identify the main stakeholders that could be influenced for this technology, in this case for the To-Syn-Fuel technology, in order to know the potential impacts and benefits of the technology and the products developed by the technology on these stakeholders. Moreover, we need to also identify the main impact categories and the main social impact subcategories in order to relate some of the impacts and benefits to these categories and subcategories. The second step of social life cycle assessment is the social life cycle inventory. Here, in this step, a collection of inventory data, which is the data needed to describe the social impacts and benefits within the system, is gathered. So during the social life cycle assessment inventory, we can gather data by using 2 different approaches. The first one, and the most suitable one, is to collect site-specific data, that means primary inventory data. And the second one is to collect secondary data, usually obtained from databases, such as, for example, the social hotspot database, which is a database we usually use in our department, and also data from literature. After all the collection of inventory data, it will start the social life cycle impact assessment step, in which all this collected data and information is translated or transformed into a resulting social impact or a risk for social impact. We usually, we can do this by determining a set of social indicators related to these social impact categories and not social impact categories. And these indicators could be quantitative or qualitative indicators, and will be evaluated or are being evaluated by using this inventory data. And these allow us to, for example, establish a rank of levels, different levels, according to these indicators, unless if they are quantitative or qualitative. Finally, the last step is the interpretation of the results, where, well, all the results are communicated, and also some improvement measures or recommendations could be also proposed. Here in this slide, you can see the first part of the work performed, which is the identification of the main stakeholders of the To-Syn-Fuel project, and also the identification of the main social impact categories that we want to be tackled with this study. You can see that we have identified 7 different stakeholder groups. First one, the workers who works in the synthetic fuel and green hydrogen production process. After this, the policymakers at local and national level. Also the scientific community, which implies university, research center, companies, research and development departments of different companies from energy sector, etc. Also the supply chain providers, which supply materials, machinery, the sewage, sludge, and other materials. The fuel producers, including international organizations related to fuel production. Consumers, which are the potential consumers of synthetic fuels for our organic biomass. And local community and society, which are the citizens and general society. So, also the social impact categories, according to the guidelines that I mentioned before, there are 6 types of social impact categories determined or proposed. Here I have selected 4 in this analysis, which are the working conditions, the health and safety, the governance, and the economic repercussions. I have selected these ones because I think that are the most appropriate ones for the typology of the project. In this slide, you can see, for example, the different stakeholder groups mentioned before, and the different social impact categories that we want to analyze. For example, related to workers, you can see that we are interested in analyzing if salary are fair salaries, the health and safety conditions, the social benefits, etc. In regards to the policymakers, for example, we want to know if the project could promote the establishment of different types of policies related to the use of synthetic fuels, renewable energy, etc. Concerning the scientific community, for example, we want to explore if this type of project could bring different type of improvements or new developments useful for scientific community in order to start other projects or other type of technologies, or putting into the market other type of products, etc. For example, for the fuel producers, one of the impacts that we want to tackle is to know if this kind of projects could bring new business opportunities and new business markets for these fuel producers, also new technologies available for them, or to improve the public commitment to sustainability issues and social issues. In the next slide, you can see that here, for example, is I am working right now on the definition of these social indicators in order to collect data to calculate these indicators. And here you can see a list of the different type of stakeholder groups and how I plan to obtain this inventory data. So taking the opportunity that we are in this conference, I want to encourage the attendance of the conference to collaborate within the project, because on one hand, for example, for the case of workers or local community or supply chain providers, I can manage the data gathering process within the project consortium or other resources. But for example, in regards to policymakers, fuel producer companies, and scientific community, I have prepared a set of interviews And we sent these interviews since 1 month ago, more or less, to different policymakers or energy experts or fuel producers in order to know their perceptions about this project, their perceptions about the use of synthetic fuels to improve and well, to reduce the greenhouse gas emissions and to comply with European targets for 2050. So I encourage you to enter to these 2 types of links according your profile or your background, and to give your opinions and knowledge in order to have data to continue with the research of the social life cycle assessment of this project. So that's all from my side. I don't know if this presentation will be sharing some point of the LBC webpage, but otherwise I can share the links in the chat.
Okay, thanks, Ariadne. Yeah, if you can help with her interviews, yeah, those links there, that would be very much appreciated. Right, the final presentation, if you could just unshare your screen, please, Ariadne, is from, yeah, thank you. It's from me. It's, I'll do that. Okay, can you see that okay?
Yeah.
Okay, thanks, Ariadne. Okay, yeah, just very quickly. So we're one of the outreach partners for To-Syn-Fuel, and as Robert mentioned right at the start, sort of as we approach the end of the project, we wanted to create a really big impact sort of public relations event. So what we're basically going to do is create a car tour of Europe now that traveling is easier, and hopefully will get easier as as the months go on. So yeah, when we're basically going to take a car that will be fueled with diesel from the demonstration plant and drive that to various locations around Europe. So this will be probably middle of September this year as the project closes. Hopefully we have the support of Volkswagen. They should be providing us with a vehicle, which is great. That's in discussion at the moment, but that looks fairly confirmed. So really just to give you an idea of the tour aims. Hang on, sorry. So yeah, obviously our main aim is to promote the To-Syn-Fuel technology, because as you've seen today, it's quite unique. It produces really high quality bio-crude oil that's very different from other forms of pyrolysis. So we really want to show how it can create really high quality drop-in diesel and gasoline. I think also, because obviously there's a strong drive towards electrification, we need to make people aware that there needs to be other contributions to greening of transport, and obviously advanced biofuels is going to be one of those, especially with regard to legacy fleet that will exist on our roads for many years, and also for larger vehicles and other vehicles that aren't suitable for electrification. We also want to address what we believe is some fairly negative public perceptions towards biofuels. I think that's the message we are sort of getting from other related projects, that biofuels are seen in a slightly negative light because of a misunderstanding of the use of feedstock. So that's something we want to address within the tour. And also we're looking to try and interact with other related projects on the tour if possible. That may be just meeting with related projects for photos or filming or something to really bring the community of biofuels together. So this is still in organization at the moment, but in terms of the route for the tour, we're going to start and finish at Fraunhofer Umsicht in Sulzbach-Rosenberg in Germany. And then the plan is to head roughly north and then anti-clockwise around Europe. Hopefully meeting with Synia or the EC in Brussels at some point. Again, that'll be an opportunity for other Synia projects potentially to get involved. Obviously, we want to connect with the partners of the project around the tour as well, and obviously meet with related industry, politicians, anyone that obviously we can meet to get people aware of the technology. We'll be filming it throughout, and we'll be creating video logs throughout, and that'll be live streamed, and we'll also produce a sort of edited video at the end of the tour that will be available for everyone to see. And as I mentioned, it's really an opportunity for other projects to get involved in other related industries. We'd be very happy to try and engage with you throughout the tour. So please just get in touch with us if you'd like to be involved in some way, even if that's just to meet with us at some point so we can talk through your technologies as well. I'd say it's all about the biofuels community as much as the project as well. So please, yeah, just it's info@to-syn-fuel.eu if you want to contact us, or just leave us a message at our project booth on the platform. And just a final slide, just to let you know, we've created a press pack on our website. That's our company website at the moment, where you can get pretty much all the information you need to know about the project. So that's the written media, some of the images and the videos. So you'll get a really good idea of what the project's about. So yeah, we'd be very happy to hear from you if you want to engage with us. So that's all I had. It's very short, but really just to really publicize that that's what we're going to be doing in September this year. I'm juggling lots of screens here. I'm just trying to see questions. Hang on. I see Maloud's put the link up for the questionnaire policy. Thanks for that, Maloud. There was one thing, as we've got a few minutes left, Robert, you wanted to address something on the nitrogen and sulfur content of the TCR crude oil, because that's obviously specific to sewage sludge. Did you want to talk through that?
Yeah, maybe it's worth to mention it, as we've seen the results from the Tcr crude oil from Stefano before. And as just wanted to mention that this is really a very specific characterization for sewage sludge as a feedstock. And then if you go for other biogenic residues as any other digestates or woody-based feedstocks, for sure, the elemental analysis is different from that. So this higher nitrogen and sulfur content is related to that. Just to underline that.
Okay, thank you for that. I don't see any more questions in the chat. So I say if you get any thoughts that come up between now and the end of Thursday, yeah, please come and visit us at our project booths, leave some questions there, or we can organize a video call with one of our technical specialists if you'd like to have a detailed discussion. So I'd be very happy to arrange that. If there's nothing else, if everyone could just turn on their screens before we go. Coming back. Okay, thank you. Yeah, just to say thank you to all our presenters today, and thank you to all of those that have attended today's seminar, webinar. So, and just to reiterate, if you want to meet with us again, come over to our project booth. So all that's left to say is thank you, and hope to speak to you soon.
Thank you. Bye.
Bye.
Bye. Bye. Thank you.
Thank you. Bye.
Bye. Bye.